All right, welcome linear algebra fans. A video today on injective linear transformations. So we'll start with the definition of what it means to be injective, see some examples. We'll talk about a new concept called the kernel. It turns out that the kernel is going to help us determine when a linear transformation is injective. We'll talk about how linear transformations that are injective are related to linear independence. We'll talk about how dimension can tell us something about injective, and we'll talk about compositions. So here's a definition. A linear transformation with domain U and codomain V is injective if whenever the image of the image of X is the image of Y, then X is equal to Y. So many of you have seen this before as one-to-one, right? Injective and one-to-one are the same thing. A common example from pre-calculus, the function f of x equals x squared plus 1 is not injective. There are lots of ways to see that this function f is not injective. One way is to take x equal to 1 and y equal to minus 1. We see their outputs are the same, right? The image of 1 and the image of minus 1 are both 2. But x is not equal to y. Okay, and to address injective, this is how we'll always start. We'll start by supposing that the image of two vectors is the same. Okay, if it must be that x is equal to y, then we see that x has to be injective. Of course, if we can find this true for some x that's not equal to y, then we know that x is not injective. Okay, so let's look at some examples. Here's an example of a linear transformation associated with archetype Q. So this is a linear transformation with domain C5 and codomain C5. And we see that, for instance, the image of this vector, I'm going to call this vector x, is equal to 4, 55, 72, 77, and 31. And similarly, the image of y is the same. Okay, since the image of x and the image of y are the same, but x is not equal to y, we see that this linear transformation is not injective. Okay, so we'll sort of see where those examples come from in a little while, but the main point here is that we've managed to cook up different input such that the output is the same, right? Different vectors in the domain such that the image is the same, so not injective. We often represent not injective with a cartoon. So the cartoon might look something like this. So here are kidney bean vector spaces U and V. Of course, we know that the 0 vector must map to the 0 vector under the transformation T. But we have two different values in the domain, x and y, such that they both map to the same value in the codomain. We'll call it T of x. Okay, so this is an example of not injective. Okay, so for this example, the linear transformation associated with archetype R will go ahead and show that it is injective. Okay, let us suppose that T of x equals T of y. From that statement, since the transformation is linear, we can come up with a slightly different equation. So if T of x is T of y, then T of x minus T of y had better be 0. Of course, this implies, since linear, that T of x minus y had better be 0. So let us just call this new vector z x minus y, and we see that identifying injective is the same as solving some system of equations, in this case equal to 0. Okay, so we can go ahead and set up a system of equations that will be homogeneous associated with this statement T of z equals 0. When you do that, there's going to be a coefficient matrix. And that coefficient matrix across the first row is going to have negative 65, 128, 10, negative 262, 40, and so on and so forth. And when you reduce that matrix to reduce row echelon form, you find that it reduces to the identity. Now, this has an implication in the case of a homogeneous system. We see then that the only solution to the related homogeneous equation must be 0. Okay, since the only solution to t of z equals 0 is z equals 0, we see that x minus y has to be 0, and if x minus y has to be 0, then x is equal to y. Okay, here's another example. Linear transformation associated with archetype V is a transformation T from domain P3 to codomain M22. And we'll go ahead and show that this is injective. And you can start out the same way by supposing that the image of some element P in the domain is equal to the image of some element Q in the domain. Of course, this implies that T of P minus T of Q is equal to 0. Similarly, since the transformation is linear, it must be that T of R is equal to 0. Okay, in this case, R is P of X minus Q of X. So similarly, we've boiled this question of injective down to the solution of a homogeneous equation. Again, I'll let you have a look at that on the worksheet, but the system of equations you get at the end of the day has a coefficient matrix that reduces to the identity. Hence, the only solution of the homogeneous system of equations is the 0 solution. So R has to be 0. So P has to be Q, showing us that T is injective. Okay, let's talk about the kernel of a linear transformation. Here's the definition. The kernel of a linear transformation T that goes from U to V is the set of all U such that the image of those vectors is the 0 vector. Okay, so this is a definition. If we want to find the kernel of T, what we'll do is solve T of U equal to 0. Okay, I'll point out that the kernel of T is a subset of the domain, right? The kernel of T contains vectors in the domain, so it's a subset of the domain. And also the kernel of T is a special preimage, right? It's the preimage of the 0 vector. Okay, so let's go ahead and have a look at the kernel of this transformation T. So to get the kernel, again, we'll solve T of U equal to 0. Okay, we can see in this case that solving T of U equals 0 is going to require us to have a look at a homogeneous system of equations. So here's the coefficient matrix for that homogeneous system of equations. We can see that it reduces to a reduced row echelon form, indicating one free variable. So we see then that the homogeneous system of equations can be written as the span of a set of vectors containing just one vector, and here's that one vector. So since solving that homogeneous system is the same as finding the kernel, we see that the kernel is the span of a set of vectors containing just that one vector. It turns out that the kernel is always a subspace. Let's have a look at this theorem. And if we want to show something's a subspace, we'll just apply theorem TSS. Okay, a quick reminder that the kernel, again, is the set of all vectors U such that the image of that vector U is equal to the 0 vector. Now, of course, it's pretty quick to see that 0 is an element of the kernel because the image of 0 is always 0, right? We know that that when T is a linear transformation, the image of 0 is 0. Now we'll just go ahead and show that our kernel is closed under vector addition and scalar multiplication. So for x and y elements of the kernel, we see that the image of x plus y is also an element of the kernel. So the kernel is closed under vector addition. When x is an element of the kernel and alpha is a scalar, we see that alpha x is an element of the kernel. So the kernel is closed under scalar multiplication. All of these steps depend on our transformation being linear, but in any case, we've shown that the kernel of T is a subspace of U. Okay, so again, since it's a subspace, and I've jumped ahead a little bit here, we can identify the kernel as a span of a set of linearly independent vectors. Okay, so in this case, we see that the statement T of U equal to 0 tells us that the only solution of the homogeneous linear system is the trivial solution. So in this case, the kernel is also trivial. Okay, if it feels like you're finding a null space of a matrix, there's a relationship here between the kernel of a transformation and the null space of a matrix. Let's have a look at this theorem. Suppose that you have a linear transformation and an element of the codomain V. If the preimage is non-empty and U is in the preimage, then we can always write the preimage as U plus any element of the kernel. So if we take W to be the subset such that everything in W is equal to U plus Z for some Z in the kernel, then the image of W is the image of U plus Z. Of course, the image of U is just V, and the image of Z is 0. So we see then that all elements of W are elements in the preimage of T. Similarly, if we have an element in the preimage of T, we can show that every element in the preimage of T is also in W. Okay, on the other hand, if Y is an element of the preimage of V, then whenever U is an element of the preimage of V, we can write T of Y minus U as T of Y minus T of U, which of course is 0, so Y minus U is an element of the kernel. Okay, so in other words, there's some vector Z such that Z is Y minus U, or similarly, Y is equal to U plus Z, where Z is in the kernel. So we see then that Y is in the set W, so that W, everything in the preimage of V is also in the set W. This is a statement of set equality and shows us that T inverse, that is, the preimage of V, is equal to the set W. Okay, so here's a proof. Suppose that that T is linear, then T is injective if and only if the kernel is trivial. So I'll prove half of this and you can prove the other half on the worksheet. Okay, we know that 0 is an element of the kernel because the image of 0 is always 0. That shows us that 0 is a subset of the kernel. The set containing 0 is a subset of the kernel. On the other hand, if x is an element of the kernel, we know that T of x has to be 0, but that's also T of 0, which tells us that x is 0 because our transformation is injective. Okay, this shows us that the kernel of T is a subset of 0, therefore the kernel of T is equal to 0, again, set equality. Okay, so I'll let you show the other way that whenever the kernel is equal to 0, then T is injective. Okay, so the take-home message here is that that trivial kernel if and only if injective. So here's an example, revisiting this example from archetype Q. We'll have a look at this element Z. We can show quickly that T of Z is equal to 0. Since the transformation T has a non-trivial element of the kernel, we see that the transformation T is not injective. Okay, here's an example we already found. We already had a look at the kernel of this transformation and found that it's trivial. A trivial kernel means that the transformation is injective. Okay, let's talk about injective linear transformations and linear independence. So here's the theorem. Suppose that we have an injective linear transformation and a linearly independent subset of the domain. Then the set containing the image of that linearly independent subset is also linearly independent. In order to have a look at this, we'll just go ahead and consider a relation of linear dependence on the set R. Okay, as usual, if the only relation of linear dependence is trivial, then the set R is linearly independent. Now, since the transformation is linear, we can write this linear combination of images as the image of the linear combination. So here's that image of the linear transformation that has to, the image of the linear combination that has to be 0. Now, of course, since T is injective, we know that the only element of the kernel is a 0 vector, so this tells us that the linear combination has to be 0. Now, of course, since the set S is linearly independent itself, this tells us that the alphas have to be 0. Okay, this is a relation of linear dependence on the set S, which we know to be linearly independent, so the alphas must all be 0, and we can conclude that R is equal to, R is a linearly independent set. Okay, so we can combine that previous theorem with a statement that B is a basis to come up with a theorem that T is injective if and only if the image of a basis is linearly independent. Okay, so again here I'll prove half of this and you can prove the other half. Okay, the proof of my half is pretty straightforward. If T is injective and B is a basis, then B must be linearly independent, right? Every basis is linearly independent. So C is linearly independent also, just by the previous theorem. So again, I'll have you go ahead and prove the other direction in this if and only if statement, assuming that C is a linearly independent set, the image of a basis is linearly independent, and showing then that T must be injective. Okay, and the way you'll do that is by showing that the kernel is trivial. Okay, so let's talk about dimension. Here is a theorem. Suppose that T has domain U and codomain V and it's injective, then the dimension of U must be less than or equal to the dimension of V. And the way that we'll prove this theorem is by contradiction. Okay, if B is a basis of the vector space U, then we just saw by the previous theorem that the set R, the image of those basis vectors, is linearly independent. Okay, so the dimension of V then has to be greater than or equal to M by the Goldilocks theorem. Okay, so this take-home message here is that looking at dimensions between domain and codomain can give us a quick test for not injective. Here's an example. We see that the dimension of the domain is 6. The dimension of the codomain is 4. Since the dimension of the codomain is less than the dimension of the domain, there's no way for this linear transformation T to be injective. Okay, again, when the dimension of the domain is greater than the dimension of the codomain, a linear transformation may not be injective. Okay, finally, just a couple comments on composition of injective linear transformations. Here's the theorem. Suppose that T is injective from U to V and S is injective from V to W, then the composition is also injective. The proof of this is pretty straightforward. So we'll show that the kernel of the composition is trivial. Okay, if U is an element of the kernel of the composition, then we see that S of T of U had better be 0. Of course, if we have an image of a vector that's 0 under the transformation S, since S is injective, it had better be that that vector is equal to the 0 vector. And since the image of a vector under the transformation T is 0, that vector had better be the 0 vector. Hence, we see that S of T is injective. Okay, folks, a lot of good stuff here. A couple take-home messages. Identifying injective requires us to solve a homogeneous linear system. Therefore, injective if and only if the kernel is trivial. Have a great day. We'll talk to you soon. Bye-bye for now.